Hello
Hello
everyone, this
everyone, this is
is Lohital
Lohital and this is
and live
live
session
session 8
of
of
introduction to.
Introduction to Interfacial Webs.
So we
So
will
we will
continue our
continue our
discussion
discussion
with
with
we will
we will
continue our
continue our
discussion
discussion
with
with
the
the
Cauchy
Cauchy Poisson
problem.
problem.
So in the
So in the
last class
last
we
class
have
we have
talked
talked
about the
about the
Cauchy
Cauchy
Poisson
Poisson
problem
problem
in
in the
the Cartesian
Cartesian
geometry.
geometry.
So
So
today we
today
will
we
talk
will
about
talk about
cylindrical
cylindrical
coordinate.
coordinate.
So
So
like
like
here,
here,
the
the
interface is
interface is
passed
passed up
as some
as some
a0 of
a0 of
a5,
a5,
where
where
a5
a5
is some
is some
arbitrary
arbitrary
function.
function.
Here a4 is an arbitrary function. So, and also initially there is some b into g of r, some function of phi is there. Now we need to determine. So now we need to determine what will be the evolution eta rt and phi rzd for these two particular initial conditions. Okay. So let's do this calculation. So like the Fourier transform in Cartesian geometry, in cylindrical geometry we have Hankel transform. It's so here if you have Fr, then its Hankel transformation is F tilde of k, and F tilde of k is defined as to infinity R J0 kr Fr dr. See, remember that in cylindrical geometry In cylindrical geometry, R only increases. R varies from 0 to some R naught. There is no minus R naught, okay, because it is cylindrical, and R will always increase from the center. It starts from 0. Okay, that's why it is starting from 0. Okay, and so if you remember the corresponding, its counterpart in the cylindrical geometry, it was minus infinity to infinity e to the power of minus ikx fx dx. So remember that in integration, while doing integration in polar coordinate, an additional r terms appear. Okay, so here you already know that in cylindrical geometry j0 kr is an eigenfunction similar to e to the power minus ikx, which is an eigenfunction in the Cartesian geometry, and here it is also fr and fx. Okay, so they are equivalent to each other. Okay, there's Hankel transformation and the Fourier transformation. Similarly, if you do want to do the inverse Hankel transformation, it will be 0 to infinity k j0 kr f tilde of k dk. Okay, so this is your inverse Hankel transformation. Okay, so now your governing equation is this is the Laplace equation in cylindrical geometry. Okay, then eta t equal to phi z at z equal to 0. This is the kinematic boundary condition. And now again I will consider only the pure capillary case. So we will have Remember, in the just go through the lecture notes of the last class. You will find that for the Cartesian case, this term was t by rho eta xx. Okay, so it is the counterpart. This is cylindrical counterpart in cylindrical geometry. Okay. Now, so this is so we only need these three. Okay, we are assuming that it is horizontally unbounded. That radius r starts from zero and it goes to it tends to infinity. Okay. Now, so initially I'm considering this condition eta r0 equal to eta 0 r and phi r0 0 is equal to some phi naught r. Okay, this is my initial condition. So just a moment. So if I define like this, so this is the normal mode approximation. Okay, e to the power of pi omega t. So now if we do substitution in these three equations, we will have 0, then this is phi z at z equal to 0. Okay, z equal to 0, and then I omega phi r0 minus p by rho e r r 1 by r, yeah, is equal to 0. Okay, now we will use Hankel transformation. Okay, so Hankel transformation means phi tilde kz is equal to 0 to infinity r j0 kr phi rz dr, and e tilde of k infinity r j0 kr e, sorry, yeah. Okay, so now let's, so yeah, and one interesting property about the Hankel transform is, so like the Fourier transform, so it was discussed in the class that, so if you do, so this is the Hankel transform phi of rz. Okay, so similarly for the Fourier transform, if f tilde of k equal to 0 to infinity, sorry, minus infinity to infinity, there was 1 by square root 2 pi e to the power minus ikx fx dx. Now if you have f double prime of x, then it will be minus k square of f tilde k, right? We know that. Now in similarly in cylindrical geometry, if you have term something like this, f tilde k, sorry, let's write g tilde of k is equal to 0 to infinity if r j0 k r g r dr, then 0 to infinity r j0 k r g r r plus 1 by r g r dr, it will give you minus k square of g tilde k. Okay, all right. So now we will substitute all this in this equation and we will finally get phi tilde zz minus k square phi tilde k z is equal to 0. Phi tilde z k 0 minus I omega e tilde of k is equal to 0. Then I omega phi tilde k 0 plus p by rho k square e tilde equal to 0. Just substitute, just use this formula and substitute in the into those three equations. You will retrieve these equations. Okay. Now from this equation we can say that phi tilde of kz will be some a tilde of k into e to the power of kz. Okay, because at z because the we need to satisfy the finiteness criteria at the infinite depth, so it will be only a tilde of k e to the power kz. Okay. Now if you substitute this in these two equations, we will get. So I'm writing the final form. We will get k tilde k minus I omega e tilde k to 0, and then I omega e tilde k plus p by rho k square e tilde. Okay, so now you have two equations and two unknown. Okay, so now you can write it in matrix form. So in the matrix form, you can write it like this. So in the matrix form, you can write it like this: k minus omega I omega p by rho k square. Equal to 0, 0. Okay. So far we have only discussed about the systems in Cartesian geometry. Okay, right. So before proceeding any further, so let me. This is probably you know all this. So this is just an extra. Okay. So let me just draw two tables: Cartesian and cylindrical. So in the Cartesian geometry, you have equation like phi xx plus phi zz is equal to 0. Here you have the equation of phi rr plus 1 by r phi r plus phi zz is equal to 0. Okay. Here, while solving, you get the equation of the form of some cos kx into e to the power of kz. Okay. And you will have some sine k, and it can also be sine kx into e to the power kz. There is no problem in that. E to the power kz, because if this is your liquid and it is minus infinity, so it is, so the result has to be finite at when z tends to minus infinity, so it is e to the power of kz. Now while solving the equation, you will find your expression like j0 kr e to the power of kz. Okay. Now j0 kr is similar to cos of kx. Okay. So if I draw the graph of you all know the graph of cos kx, right? So so For J0 here, the plot looks like this. It is also an oscillatory function, but it decays. Okay, if this is R and this is J0 of KR, as R increases, the oscillation, the height of the oscillation decreases. Okay, and derivative of this J0 KR is J minus J minus KJ1 KR. So derivative of J0R is uh, minus J1R. So now if I draw J1 of KR, it is related to the sine. Okay, which is just related to sine of x. So for this, the curve look like this. So it starts with some finite value, but it starts with 0. Okay. So just remember this. So it is just related to sine and cosine. Okay. So this is the basic thing for the cylindrical geometry. Also, while solving this, if you search in Google, you will find that there is also a solution called Y0 of KR. Okay. This can be a valid solution, but you have to apart from this finiteness criteria, see if I draw the cylinder, okay, now j the problem of y not kr is it diverges at r equal to 0, but physically it is not possible, right? It must have some physical solution. Okay, if at r equal to 0 it diverges, then it is not physical solution, so we just remove that part from our solution. Okay. All right. So we will discuss about it in the future videos that in detail. But let us now again go to the Cauchy version problem. So far I haven't used too much about in the too many things regarding the cylindrical geometry. Only the fact that here, so the if double prime x just converted to this something like this, and its Hankel transform is just similar to the Fourier transform minus k square g tilde of k. This is one important part in important criteria of the cylindrical geometry that I have used so far. Okay. Other things are just similar to the case of the Cartesian geometry. So now if you have equations like this, so now to get a non-trivial solution, so you need to calculate the determinant of the system that will give you the eigenvalue. Okay. So if you calculate a determinant, you will find omega square is equal to tkq by rho. Okay. See that it is already in a minus lambda I x equal to 0 form. Okay, so you just need to calculate the determinant and you will find what is unknown here. Omega is unknown, and you will find what is omega. Okay, because that is our main criteria, right? We are from the normal mode analysis, so we try to find what is frequency of the system. So now, so there will be two values. So maybe omega 1 equal to positive 1 TKQ by rho. Okay. So let us define let E tilde of A is equal to C of CK. So we will have So here if we put ck is equal to I square root of pk by rho and a tilde k is equal to 1, then they satisfy each other. Okay, so one solution can be e tilde is equal to 1. Mm, sorry, if I put here 1, so I can write ck tilde ck equal to a tilde k times I tk square root tk by rho. Okay, so I can write the solution like this. Mm, no, let's just do like this. So from the first equation we have k into ck minus equal to I square root of t k cube by rho a tilde of k. This implies ck equal to I square root of tk by rho a tilde of k. Okay. Now remember omega 1 equal to square root of tk cube by rho. So write this as I. Okay, am I making some mistake? Oh, yeah, I am making some one mistake. So it will be a tilde of k. It will be c of k. Okay. So it will be just opposite. It will be a tilde of k. It will be c of k. C of k. So if omega is tk cube by rho, so I can write a tilde of k equal to 1 by k I square root of p k cube by rho ck I omega by k c k. Omega 1 t equal to omega. Okay, and omega 2 say equal to minus omega. So I can write a tilde k c k equal to e tilde k, sorry, equal to this constant may come out times I square root of t k by rho and it will be 1. Okay. Now for omega equal to minus square root of tk cube by rho. Okay. So here we will again do the analysis. So here we will have k times I square root of tk cube by rho and rho. A tilde k e tilde k equal to 0 0. Here let us assume e tilde k is equal to some constant b of k. Okay, and you will find that k of a tilde k is equal to minus bk into I square root of tk cube by rho. And if we consider like this, that a tilde k is equal to this constant pk outside minus I square root of pk by rho and 1. then you can see that both these two equations will be satisfied. Okay. So as a whole, so this is one equation and this is the other. Sorry, one solution and another solution. So as a whole, we write it like this. We can write it like phi r z t theta r t equal to 0 to infinity ck I square root of t k by 2 e to the power a z 1 e to the power I omega t. Okay. So this will be, so this is the r part, this is the k part and this is the z part. So I am writing the whole thing I omega t plus k minus I square root of tk by rho e to the power kz 1 e to the power minus I omega t j0. So this is inverse angle transfer j0 kr into k dk. Okay. Now initial condition we can write. So it will be phi r00 eta r0. So it will be phi 0 of r now eta 0 r is equal to 0 to infinity ck by rho 1 plus dk minus of I square root of tk by rho 1 j0 kr k d k. It is all of that. Okay. So comparing this, we will get this left hand side and the right hand side. So now, so also see that so we have this. Okay, so this right hand side, it is coming from this equation. Also now we can convert it like this. See that if we can write it like this, we can write it like 0 to infinity is equal to 0 to infinity. Uh, Phi 0 tilde k eta 0 tilde k j0 kr k d. Okay, so I can write this in this form, in the inverse Hankel transformation form. So if I consider this right hand side and the left hand side, I will get ck minus dk I square root of tk by rho is equal to phi tilde of k, and ck plus dk is equal to eta 0 tilde of k. Now from this equation I get, so if you take it to that side it will be minus I. Okay, because it is plus 1, so minus I squared is plus 1. Hmm? Okay. Now okay, and I have ck plus dk equal to this term. So as a result, you will get finally ck will be equal to half eta 0 tilde k minus I square root of rho by pk phi 0 tilde k. Okay, and dk will be equal to half eta 0 tilde k plus I square root of rho by t k phi 0 tilde of k. Okay. Now, if you consider a special case, okay, that means initially you have no velocity potential, huh? Then your phi 0 tilde of k will be 0. Then you will have, so if phi 0 is equal to 0, so you will have ck is equal to half of eta 0 tilde k. Okay. Now, for that case, you will have, so what you have to do, so now you have found what is ck and dk. Now you just need to substitute in this equation. Okay. So now I will consider only the case where there is initial perturbation but no initial velocity. Okay. So you do the calculation for when you have initial perturbation, initial velocity both. Okay. So now then I will have phi r z t. I will substitute ck and dk in this equation. So I will have 0 to infinity half eta 0 tilde of k into I square root of tk by rho e to the power I omega t minus of e to the power I omega t j0 kr k dk. Now we can simplify it. Okay. It will become 0 to infinity eta 0 tilde of k into tk by rho and e to the and e to the power I omega t minus e to the power minus I omega t, it will give you into 2i sin omega t into I into j0 kr k dk. So and there is one term divided by 2. So finally you will have minus 0 to infinity square root of tk by rho eta 0 tilde. Oh, sorry, there is one e to the power kz term that I missed. Eta 0 tilde k e to the power kz j0 kr and omega t k dk. Okay. So this is, so you just need to feed eta 0 tilde. So this is k and omega is already determined. So for any kind of system where your eta 0 is specified and phi 0 is 0, so you can find the solution, right? Similarly, if you do the calculation for eta rt, you will find, so for the eta rt is simple. It will be 0 to infinity half eta 0 tilde k e to the power I omega t plus e to the power of minus I omega t j0 kr k dk. So it will be half eta 0 tilde k into 2 cos omega t j0 kr k dk. So it will be 0 to infinity eta 0 tilde k cos omega t j0 kr k dk. Okay. So this will be your final solution for eta rt and this is your solution for phi rz. So if you get some arbitrary perturbation initially, then you can find the solution of this case. Okay. So I will show you one case, one particular initial condition, that is if your eta 0 of r is equal to some a0 by r into delta r. Okay. Then your eta 0 tilde k will be 0 to infinity r a0 r into a0 by r delta r j0 kr dr. So r will get cancelled. So you will finally get a0 is a constant, a0 0 to infinity delta r j0 kr dr. Now delta is delta, so delta is 0 everywhere except r equal to 0, right? So the finally you will get the result of a0. Okay, finally this will be your solution. So for this case, for this particular case, you will have phi r z t will be equal to minus a0 0 to infinity square root pk by rho p to the power kz j0 kr k dk tk cube by rho x t and eta rt is equal to a0 0 to infinity cos square root of tk cube by rho j0 kr. Okay, and you can solve it in various ways. Just the easiest way will be use numerical integration, and you can find a calculation. Okay. Also, you can try one more function that I am giving you. Try this function eta 0 r. So this might be a homework is equal to a0 into 1 minus r by b square e to the power minus r by b whole square. Okay, you can find it Hankel's. So try for this initial condition and see what is the how so what is the so and try to find the evolution of your interface. Okay, you can numeric one thing you can do how to, so one thing obvious question is how to find its numerical Hankel transform. One thing you can do, you can use numerical integration technique, or you can use some mathematical toolbox like Mathematica to find its eta, to find its eta 0 tilde of k. Then you can fit in these equations, okay, to find its evolution in time, right? You can also try for you can try and find what is the Hankel transformation of j0 kr. Yeah, so that means so j0 kr is the eigenfunction in cylindrical geometry. You can feed it, and you can try to find what will be the evolution for the j0 kr as well. Okay, yeah. So that's all for Cauchy boson in cylindrical geometry. Okay, now, so although you will learn about the spherical geometry in the probably the next or next week. But but while we are doing but while we are solving uh, Cauchy boson problem, so I will also talk a little about the Cauchy boson problem on spherical geometry. Okay, so suppose you have this initial condition like this, so and you have slightly part of it. Okay, it is not erasing. Okay. So you have and you have part of it something like this. Okay. So this is just to year of a cat. You can think something like that. You have give something perturbation like this. Okay. Then you ask the question, what will be the evolution of the interface? So obviously this is a spherical geometry. So whatever we have done so far in Cartesian coordinate, in cylindrical coordinate, now we have to do exactly the same exercise in spherical coordinate. Okay, the idea is same, only the geometry is new. So you need to learn few new things about it. Okay, but all the other methods, they are the exactly same. So I will give you the solution. So I will write you. So I will give you the uh, procedure how to solve it. So even if you do not understand, if you are not familiar with spherical geometry quite well, but you can learn it. But you can learn it just by just Google it, and you can find all the things you needed. But the main idea is that you have some arbitrary perturbation, and you have to use Cauchy boson problem. And and all other governing equations and the boundary conditions are exactly same as the cylindrical or Cartesian geometry. Okay. So let us do the solution. So, so in spherical geometry, we need to just a moment. So the calculation might be little lengthy, but just keep it in hand, so it will be helpful for you. So, so in spherical geometry, the governing equation will look like this. So it is axisymmetric. Okay, so there is no so there are three angles. Okay, this is one angle theta. This is r. This is one angle phi. So there is no phi dependent in our case. Okay, so this is axisymmetric. So this is around the circumference phi, and phi is varying from 0 to 2 pi, and theta is varying from 0 to pi. Okay, so there is no phi dependent in our calculation. So we will treat phi as velocity potential. So phi r plus 2 by r phi r plus cot theta phi theta plus phi theta theta is equal to 0. So there is also theta phi. Oh, I have forgotten this one. Theta. Okay. So if we now substitute as x equal to cos theta. Okay. Suppose x equal to cos theta. Theta I have previously talked that the theta is this angle, polar angle. So dx equal to minus sine theta d theta is equal to minus square root of 1 minus x square d theta. So d d theta is equal to minus of 1 minus x square d dx. So this is just simple substitution so far. Okay. So d square d you will see immediately you will see what is the benefit of this substitution. So d square d theta square is equal to minus of d dx 1 minus x square d, dx. Okay, so let's move on to the next page. So if you do the calculation, you will finally get this result of 1 minus x square d square dx square minus x d dx. Okay, so we have now completely changed the theta dependence to x dependence. So we will get r square times phi r plus 2 by r phi r plus 1 minus x square phi x minus x times phi x is equal to 0. Okay. So now, so what I will do, so we will do the spherical geometry in detail later, probably in the next week or next week. So what I will do, I will just give you so the key point of this, the key idea of this Cauchy Poisson and spherical geometry. So again, you need to do what you need to do something like this. So here we don't have any theta anymore. We have r and x, rx and t. So you need to just do again normal mode analysis and theta x t is equal to ex. It will go to y omega. Okay. So here, so similarly to the Fourier transform, and Hankel transform, you will get Legendre integral transformation. Legendre integral transformation. Okay. So now, so as we have converted x to x as cos theta, and theta varies from 0 to pi. So here your your phi tilde, it is defined as minus 1 to 1, because cos theta at cos pi it is minus 1, cos 0 is 1, so it will be phi rx, and there is some function called pnx that you will learn about it later, and p tilde is equal to minus 1 to 1 ex pnx dx. So this is called Legendre function, Legendre polynomial. Okay, so there are so you so if you so just see any any math book, you will find all the expression regarding the Legendre polynomial. P1, P2, P3, they all have different kind of expression. Okay, so now you need to use this transformation in your system, in your spherical geometry, and you need to, and then after that you will be able to find a solution, and finally you will exactly get a exactly get a solution based on this n. And if we provide any and if we provide an arbitrary initial condition, then you will be able to find your then you will be able to find your solution for that. Okay, so what so as you haven't learned about the oscillation in physical geometry, so what I will do, I will just post, I will send you this note. I will say, I will generate and I will create a write up on the Cauchy version problem in spherical geometry, and I will post it, and then after that you can read it and you will understand what is happening here. But the key idea is this: similarly to the Fourier transform and Hankel transform, in spherical geometry you need to use. So it is in spherical, you need to use Legendre integral transformation. Okay, so that is the most key idea. So the geometry is complicated, so the calculation is little bit complicated, but all other idea those are the same. Just a moment. Oh, so so you will understand these things better when you are at week 10. Okay, so there you will there you will learn about. So there you will learn about the spherical geometry, oscillation, and spherical geometry. Then you will understand these things better. Maybe I can, maybe I will take few minutes to discuss this thing again, but I will send you the write up. So now what we can do? So so now let's so we have discussed a sufficient amount of thing about regarding the Cauchy version problem. So now let us solve some example problem. Okay. So yeah, so we will solve the questions on assignment 8. So so okay, so first question is select the correct statement. So phase velocity Cp is related to the energy propagation of a wave. Energy propagation of a wave. Okay. So you know that the relation that daily del t plus del x of Cg is equal to 0. It appears for the propagating wave. Okay. Here Cg is the group velocity. Okay. So group velocity is related to the energy propagation of wave. So option B is your correct answer. Okay. So so now this question for infinitely deep. Okay. So what is the formula for Cg? Cg is your d omega dk. Okay, so you can see the derivation. It is coming from the fact that omega by k to d omega by bk because we are considering many waves. Okay, and which have difference in frequency and difference in wavelength. So as a limit, we get this expression of d omega dk. Okay, now for infinitely deep gravity waves, what is the governing equation? Omega square is equal to gk. So omega is equal to your square root of gk. So now phase velocity is your square root or say g by k. Now what will be your Cg? Cg will be your d omega dk is at half square root of g by k is equal to Cp by 2. So Cp by Cg will be U2. Okay, that means the space speed is higher than the group velocity. Now, for infinitely deep capillary waves, okay. So, what is your omega? Omega is your pkq by rho. So, your c is square root of cp. Pk by rho that is equal to omega by k, and cg is equal to d omega dk is equal to 3 by 2 square root of pk by rho, huh, is equal to 3 by 2 cp. So Cp by Cg is equal to 2 by 3. So your option C is correct. Okay. Okay. So now, while we are doing this, let us also take a look at what happens at the finite depth. Okay. Suppose you have a problem where you have finite depth. And pure gravity. So what is your omega? We have derived it. It is omega square equal to gk tan h kh. Kh capital H. H is a depth. Okay. So omega equal to square root of gk tan h kh. So phase velocity, phase speed will be cp square root of g by k tan h kh. Okay. And yeah, for group velocity Cg, you need to do some more work. Cg is equal to d omega dk. So now what is tan h? So what is the derivative of tan h is? I forgot. Let me just check. So your ddk of tan h kh is equal to kh. Okay. So this will be your so this will be a formula. So what will be your CG? CG will be square root g is a constant into half to okay half into 1 by square root of k tan h k. So this is a complicated expression into into tan h k h plus k h 6 square. Just check the expression. It is possible that I might have made some mistake. Okay, so but this will be approximate expression for the finite time. Now, if we go to the shallow water limit, okay, your omega square will be equal to gk. So tan h kh will be kh. In the last week we have discussed it. It will be g times k square h. So this is non-dispersive, right? So omega equal to square root gh into k. Now for the non-dispersive, there is one property that is Cp will be equal to Cg. Okay, because without dispersion, that all wave packets will move at the same speed. This is the whole idea of the non-dispersible, right? So so for the shallow water limit, by this way we can prove the Cp that it is non-dispersive and Cp will be equal to exactly as C. All right. So now let's solve this question 3. So So what we have in question 3 that if a resultant wave is created by linear superposition of two propagation waves, that psi 1 is cos 1.95x minus 30.3 p. So there is one wave like this. It is traveling at some speed, and there is another wave which is traveling with some. So this is a cosine. So I have drawn that sign, but okay. So, so let me draw it clearly. It will be something like this. So it is a cosine wave. It is it is propagating and with some speed. Okay. So okay. So phi one is cos 19.5 1.95x minus 30.3 t, and phi two is 2.05x minus 29.7 t. Okay. So what we can do? Uh, so then what will be the propagation speed of the resultant wave length? Okay. Now, so here your K average. So this is something like kx minus omega t, right? So K average will be 1.95 plus 2.05 divided by 2, and this will be equal to 2. Okay. And your omega average will be equal to 30.3 plus 29.7 by 2 is equal to 30. Okay. So now what will be your delta omega by delta k? Delta omega delta k will be your deviation from this average wave number. So it will be, so say 2.30.3 minus 30 by 2.05 minus 2, and if you find the answer, the answer will be your 6. It will be 6 centimeter per second. It will be your average group velocity. Okay, see that this is delta omega by delta k is proportional to d omega dk. Okay, delta omega. So delta omega by delta k is approximately equal to d omega dk. Okay, so this is the whole idea. So your correct answer will be D. Also, you don't. It is not necessary to calculate this average. Okay, just find delta omega by delta. Just do the delta omega by delta k for these two waves, and you will just find the answer 6. Okay, it is not necessary to calculate k average. Okay, so now we need to solve question 4. Question 4 says we have to find a relation between CP and CG for any arbitrary wave number. So this is CP equal to omega by k. Okay. CG equal to b omega e g. Okay. So so yeah. So if this is k, if we just substitute this, we will get d omega by d of omega by cp. Okay. Now d of x by y is equal to y dx minus x dy by y square. So we will get d omega divided by Cp d omega minus omega dCp by Cp square. Okay. So what I can do, I can let me multiply. So it will be Cp square d omega by Cp d omega minus omega dCp. So now if I divide it by d omega, I will have Cp square by Cp minus omega d Cp d omega. Okay. Now I can also again divide it by Cp. Then I will get Cp. If I divide both the numerator and denominator by Cp, I will get Cp minus 1 minus omega by Cp into dCp d omega. Okay. And your omega by Cp is equal to k. So I will get Cp minus 1 minus divided by 1 minus k into dCp. Okay. So what will be correct answer? Correct answer will be dCp d. This will be your correct answer. Okay. Okay. So now, okay. So right. So now you need to find what is the graph for c square versus k. Right, in the for the capillary gravity waves. Okay. Now first let me write down the equation for the capillary gravity wave. We have discussed it in the last class. That is omega square is equal to gk plus tk by rho. Now c equal to omega by k. So c square will be equal to b. So now we need to divide it by k square. It will be g by k plus tk by rho. Right. Now, right. So now we have to draw this. Now, okay. So now there are two parts to it. So one, so when k is very large, When k is very large, it will be also, we can see that this term, this this is 1 and this is 2. Okay, so let us consider two different cases, right? When k is tends to infinity, then 1 is approximately 0 and 2 is approximately infinity, but this is linear, right? When k is large, then it will be linear profile. So it will be something like this linear profile when k is large. It will be, so let me draw it here. It will be linear profile like this when k is sufficiently large. Okay. Now, when k is small, then I tends to infinity, right? And what will be the nature of the curve? Nature of the curve will be a hyperbola because xy equal to some constant kind of curve will appear. It will be some hyperbola. Okay, and 2, when k is small, 2 it will be tends to 0. Okay, so the curve will look something like this. So the curve will look something like this peculiar looking curve. It is c square and it is k. So in the last class, I have discussed about a particular limit, particular wave number, above which it will be capillary dominated and below which it is the gravity dominated. So let me do that again. Okay, and from the graph you can explicitly understand what is happening. Okay, so see that there is a particular region, particular joint above beyond which it is almost linear, and and before that it is hyperbola, right? And the part where it is linear, the term is tk by rho. So just do it graphically. It is tk by rho, and the equation for the parabola is g by k. Now when they are almost same, at that point, if I try to do this, so if I try to find what is the value for that, it will be g by k is equal to tk by rho, right? So your k square is equal to rho g by t. So k will be equal to square root of g rho by t. Now if you try to find it for air water parameter, okay, air water interface, you have for gravity will be constant, but for in r on r it will be 981 in cgs unit, and p will be 72 again in cgs unit. So if you do the calculation, you will find 981 and rho is 1 for water, okay, by 72. So you will find your k is approximately equal to 3.7. Yeah. So beyond 3.7, so this point that we have found here, it is 3.7. Now beyond 3.7, it is capillary dominant because you can see that this is straight line and it k and its slope is t by rho. Huh? So this is capillary dominant. And before 3.7, it is gravity dominated because gravity is present. Okay. Now now what is the meaning of k is going higher? K is going higher means your wavelength that is decreasing. Okay. Remember the case we have discussed in the Rayleigh-Taylor instability. Huh? When if we make the continuous size small, even when the higher fluid is on top of the even the denser fluid is on top of the lighter fluid, the system can be stable and surface tension does that thing. But remember the criteria that the radius has to be small. That means your k has to be sufficiently large because k is your inverse of your length, right? This is the it is centimeter inverse or meter inverse. It is wave number. So there it is capillary dominated. That means it was in somewhere in this regime. Huh? But 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 this is your gravity dominated regime. Okay, so this is in this hyperbola, in this hyperbola region. Okay, so in the last class I was told about I discussed about this thing. Now here from picture, so here from the picture we now we now can estimate what will be the optimum k beyond which the system can be capillary dominated or gravity dominated. Okay, all right. Now, linear dispersion relation for an infinitely deep free surface gravity waves are similar in Cartesian and cylindrical coordinate. Cylindrical coordinate counterpart Fourier transform is Legendre transform. Cylindrical coordinate counterpart of Fourier transform, Hankel transform, all roots of J0 are equidistant. So these okay. So now we can discuss. So we have done some work regarding the cylindrical geometry, but let me show explicitly one solution, but which is not a any special kind of initial condition. I will start the initial condition by, by taking initial perturbation as J0 of Ki. Okay. So right. So one thing that we have already told that J0 is similar to cosine in Cartesian geometry. So what is the governing equation in cylindrical geometry? Phi r plus 1 by r phi r plus phi zz is equal to 0. I will assume that the radius is it is infinite, radius is infinitely large. Okay, and z is also tends to z is also very large. The vertical height I will assume infinite, it is infinitely deep. So I will have two more boundary conditions. Let us consider for the pure gravity. Okay. So what was the question? Is it regarding the pure gravity or both gravity and surface tension? Yeah, surface gravity. Yes. Okay. Right. So remember, in the Cartesian geometry, we had omega squared is equal to gk. Now we'll try to find what we will get here. Okay, so it might obviously so we have already found this in the Cauchy version problem. But let me solve one small example. This is a very small exercise that is where I am starting with a good initial perturbation. Okay. Uh, also you can do one exercise that uh, in the expression in this expression uh, you will find what is the Hankel transformation of J0 of some kr. Okay, we try to plug it in here and find the solution. You will find that now the method that I will follow, that is our common method. So common method that we have done in the last class. And if you do that by Cauchy version problem, you will exactly find the same solution. Okay. So this is one equation, that is the Laplace equation in cylindrical geometry. The other equation is del r del phi del z is equal to del eta del t at z equal to 0 and del phi del t plus z eta is equal to 0. Right? So, what is the solution of this equation? The solution of this equation that we have already discussed, that it will have the form like this. So, I will take one case is equal to a, some constant a, j0 kr times e to the power of kz. Hmm? So, now you need to be acquainted with one property of this special function, that uh, this d squared dr square of j0 square j0 kr plus 1 by r dr of j0 kr is equal to minus k square j0 kr. Okay. Huh. This is one correlation. Okay. That you can see on internet. So this is one correlation, and if this is so you have to use this in this equation, you will find that this is exactly satisfying this equation. Okay, there can be other solution related to y naught kr into e to the power kz, but as I have told already that y0 kr is y0 kr is will diverge at r equal to 0, so we do not consider this solution. Okay, so we consider only this solution. Also, I have already implemented the finiteness criteria. At z tends to minus infinity, this value has to be finite. Okay, next. Okay, so now see this equation: del phi del z is equal to del eta del t. So the temporal dependence, and so the spatial dependence or r direction will be same for eta and phi. So for eta, I can take like this. Okay, so it will be phi rz times t. So I will take this as a of t, a t. So eta t I can take eta rt. I can take something like this a t j0 kr. Okay. Now from the first equation, I will get k times a t is equal to del eta del t is equal to a dot. Okay. And from the second equation, I get del phi del t. That means a dot t plus g into a of t is equal to 0. So here I get that a t, here it is a dot t, okay, is equal to 1 by k small a dot t. So if I substitute it, I will get a double dot by k plus g a is equal to 0. This implies a double dot plus g k a equal to 0. So this is your frequency here. This is omega square. So just see the notes of the last class. We have defined this as omega square. It is equal to your gk. Okay. So we find that in cylindrical geometry as well, your frequency will be same as the Cartesian geometry. Okay. So if you do this exercise for the capillary waves also, you will find that for the at the linear order, the frequency for the cylindrical and the Cartesian geometry are exactly the same. Okay. Okay. All right. So now Let us go to the question. So linear dispersion relation for an infinitely deep free surface gravity waves are similar in Cartesian and cylindrical coordinate. This option is correct. Option B, cylindrical coordinate counterpart Fourier transform legendary transform. No, 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 this is not. Legendary transform is for the spherical geometry, not cylindrical geometry, right? And cylindrical coordinate transform or Fourier transform, Hankel transform. This is right. This option that you need to know, okay, you can find the roots of j0 numerically, and so I have told that j0 is similar to cos, right? But the difference is for the cos, you will find 0 at pi by 2, 3 pi by 2, 5 pi by 2, right? So if this is cos, if its roots are something like this, this is maybe pi by 2, this 3 pi by 2, 5 pi by 2. So they are equidistant. Huh? But for Bessel function, the roots are not equidistant. Okay. So this option is incorrect. Okay. So, so now we will now solve the last question. Okay. Right. Hmm. So you have this expression fx equal to a into sine x minus 1 plus b into sine x minus 3. Then on the f tilde k versus k plot in Fourier space, where will you find peaks? So what is f tilde of k? It will be 1 by square root 2 pi infinity e to the power minus I kx fx dx. Okay. So it is something like this. Okay. So if I take the first term only, so sine x minus 1. right? This is the term. So how can I write it? So I can write it like this: e to the power I x minus 1 minus e to the power minus I x minus 1 divided by 2y. Right? I think I can write it in this way. So if I substitute this, I will get something like mm, okay. So assume k greater than 0. Okay, so k greater than 0. So k is only positive. Just a minute. Okay, so before doing this exercise, so suppose we give you a function like this, that xt yx equal to sine k naught x. Okay, if I give you this function, okay, so so how can I write it? I can write it like e to the power I k0x minus e to the power minus I k0x by 2y. Okay, so now what is the Fourier transform of this function sine k naught x? So I can write it in this way, that is equal to minus infinity to infinity e to the power minus I kx into e to the power I k0x minus e to the power minus I k0x by 2y times dx. So it will be equal to 1 by 2i minus infinity to infinity e to the power minus I k minus k naught x dx and minus 1 by 2i minus infinity to infinity e to the power minus I k plus k naught x dx. Okay. So now again we can write it in this way. So again this is a kind of a Fourier transform of 1 by 2i f of mm, t. So this is a Fourier transform of e to the power I k0x minus 1 by 2i Fourier transform e to the power of minus of I k0x. Okay. Now This is so. This is something new to you. Though this value is proportional to is delta of k minus k naught, and this value is proportional to delta k plus k naught. Okay, so there will be some prefactor of 2 pi, square root of 2 pi. Okay, so we can write it as some constant c1 delta k minus k naught plus delta some c constant c2 k plus k naught. Now we know the property of the delta function, right? So it will give you peak at k equal to k naught and minus k naught. Okay. So when you have provided this expression sine k naught x in the Fourier space, you will see peak. No, if this is zero. Suppose this is some value of k minus one, k0, k1, k2. Again, minus of k minus one, minus k0, minus k2, k1, something like that. You will get two peaks at k0. Okay, this is coming from the fact that this is k naught minus x, huh? Sine k naught x. Okay, so you will get two peak at k naught and plus k naught and minus k naught. Okay, so in the other it is just nothing. So in the Fourier space, the Henkel, the Fourier transform sine k naught x is a delta function. Okay. So what you can do, you can try to find a cylindrical counterpart. You can try to find what will be the Henkel transform J0 of k naught r. Okay, you can try that at home. Okay. So now, now I think there is a problem with the question. Okay, I have to check it. But suppose you are driven with some expression like this: fx equal to a into sine x plus b into sine of 3x. If you are provided with this kind of expression, huh, then your Fourier transform, I will check this equation and tell you in the next week if this expression is correct or not. But suppose you have an expression like this. Okay, now we have done a similar solve a similar problem. So if your f tilde of k, so what will be your f tilde of k? F tilde of k will be some constant into delta k minus 1 plus c2 delta k plus 1. Okay, this is coming from this plus some c3 delta k minus 3 plus c4 delta k plus 3. Okay, so you will get this expression. Now it is told if your k is greater than 0, then you will find two peaks at k equal to 1 and k equal to 3. This is 1, this is 3. Okay, so you will find this expression. Okay, uh, just a second, huh? So now suppose you have some expression. So now if you have some initial, this is for sine. If you start with an initial condition of sine of something x. Okay. Now Now if you start with some a function like this, that fx equal to your cos of k0x. Okay, so so what will be the solution? The treatment will be exactly the same. We will write it at e to the power I k naught x plus e to the power minus of I k naught x by 2, and you will do the Fourier transformation, and you again find it will be something like delta k minus k naught and delta k plus k naught. Okay, so only the new thing to you is this definition that Fourier transform of this function is this one is a delta function. Okay, in the next class I will try to physically describe why this is happening. Okay, so yeah, so that's all for today. So in today's class we have discussed about the Cauchy poisson problem in the cylindrical geometry. Also I have talked about a little bit about in the spherical geometry, but I will talk about it in more detail when you have done after week 10. But anyway, I will share the note regarding the Cauchy poisson on a sphere, and then we have solved the assignment problems. Now for the so now so yeah so just so now your task is to just do the counterpart in the cylindrical geometry. If you try with a J0, J0, K0, J0 of some K0 of R, then what will be the final solution? And also, yeah, and also try to find a solution numerically where you some take some arbitrary initial guess of eta 0 1 and find eta tilde of k, and then do solve this question numerically. Okay, and in the next class I will try to provide a physical explanation for this, why this is happening. Okay, and yeah, and I will share this lecture notes and video with you. So I will meet you in the next week.